There's science behind everything. There's molecular literacy behind everything. Instead of kind of thinking science is for disease and for energy and then for helping the environment, look at it all around. Storytelling creates impact, it creates joy, creates a space for imagination. Storytelling, putting a vehicle to get to their imagination so that the molecule can then become something that they can see. In chemistry in particular is what storytelling does. So it builds all of that. Definitely the imagination part, I think, is the most important.
Welcome to the Science with Impact podcast. Why should our audience, who are research scientists looking to broaden their societal impacts, listen to our conversation today?
I think it comes down to that we're all on the same team and we all recognize the need for a rebrand. And molecular literacy gives grace to everything that's happened before. When we recognize that these failure rates and these trauma experiences and all of this is a result of a literacy problem, which is significant, but we know now that we can circumvent it or get around it or address it. That's why they should listen to it, because we all need to be part of this rebranding and we all need to understand, okay, if someone has a bad experience with chemistry, it's probably because they're molecularly illiterate. How can I explain it in a way that's literate? And how can I build that? So how would I explain something to a child who can't read a book, but needs a story to be told to them?
And if they listen to this episode, they will get so many different examples of how you've succeeded in doing that. I'm so grateful to have Colleen here. Colleen, could you please introduce yourself to our audience?
Yes, I'm Colleen Kelley, and I'm the creator and founder of a comic book series. We have a series of comic books that scaffold the learning objectives found in a 100-level college chemistry course. So if you look at a traditional textbook for a Chem 101 at any college or university, what I've done is I've taken each of those chapters and created one comic book out of each chapter, so that when you look at the chemistry comic books in tandem as a series, it is the equivalent of a college chemistry textbook, only in comic book format. What I've done is created this format that makes learning chemistry accessible to anyone because of the format, but also to remember that we're doing big league chemistry. Even though there's cute characters and fun jokes and all kinds of stuff going on, we're still learning introductory chemistry 101. I love to put that forward because when you look at the offerings of what's up there, some viewers and people immediately looking at it think, well, that's for elementary school, which it is. And that's why I have my very cheeky saying, molecular literacy for ages 8 to 108, because I firmly believe that if you missed the boat or somehow didn't enjoy chemistry, which is a lot of people because I taught thousands of them in my 30 years in med, go back and try it with this comic book series. It might be a better way for you to learn. And I'm really focusing on teaching chemistry like we teach reading, and really focusing on the literacy part of that and what that means and what that can bring to the table. So I want to capture the 8-year-olds, and I want to capture the 108-year-olds who say, you know what, I failed chemistry in high school and college, but I think I would really want to know how to balance a chemical equation or something like that. Pick up my curriculum and that'll do it for you.
How do you know me? Science with Impact.
I've been following you on LinkedIn and social media, and we share some common connections. The American Chemical Society, the Green Chemistry Institute. So shout out to all those folks doing a lot of great work, and they're persevering. And I'm just so proud to be connected with this group.
The one thing I've noticed with every scientist that I interview for the podcast is we tend to have kind of an assortment of experiences that were impactful in eventually defining our trajectory as becoming scientists. Could you outline some of those for me, for you?
Yeah, I am a first-generation college student. And when I was in high school, the family plan was for, at the time, I was in high school in the 80s, so we were called a secretary. So I was taking typing lessons and developing all the skills to become a secretary. Now it's called an administrative assistant, but at the time, that's still what's in my mind. And so I was being groomed for that as a career. And I was in high school chemistry and just loving it and thinking, I do love typing, it's kind of fun, but I really love chemistry, and I wanted to go to college, and I was always a good student, I was getting good grades, so I figured out a way to pay for college myself and get myself there and become a chemistry major, and probably the turning point for my life was not just getting to college, but was my best friend in my college chemistry freshman class said, "Hey, I'm going to stay for the summer and do research." And I said, "Hey, what's that?" And she's like, "I don't know. You stay and you work with a professor." And, I had no idea what she was talking about, but kind of got the gist of it. And she was an awesome friend. So I just took myself up to the second floor of Gottwald Science Center at University of Richmond, sat in front of Dr. Emma Goldman's door because this was before email, folks. I couldn't email her or really even call her. So I just sat in front of her door and did my homework until she eventually showed up. And I just introduced myself and I said, so naively, "I would like to do research with you," not having any idea what that even meant or anything. She said, "Come in," and she had all these binders full of articles and was showing me her research and explaining it to me. And I thought, well, this is cool. And then she showed me a chemical reaction that I would do if I was in her research group. And then she said, "No one has ever done this before." And I thought, like, I would do something nobody else in the whole world has ever done before, and I didn't know that's what research was. I was so naive, and she was so kind. I stayed that summer and kept doing research and loved it, had a blast, and when I was ready to graduate, she said, "You should get a PhD." And I just said, "Okay, what's that?" And so it just kept going. I didn't really have a plan. People just kept suggesting stuff to me, and I just kept saying yes, basically.
Can we back just a bit? You're there, you're typing, you're learning to be what was called a secretary at the time, and you think to yourself, like, chemistry is cool. Tell me more about like what were those initial early experiences that you had with chemistry? It sounds like it wasn't very common, maybe for women to pursue chemistry. Is that true? And what led you to being able to believe that you could do this?
I had been told by teachers and adults that I was whatever, smart, right? You get this label, and I don't know what that meant, but I had that label. So there was some academic confidence because I had kept being told that, and my report card seemed to reflect that. This is how I was labeled as a 16, 15-year-old. So I thought, well, I'm pretty confident in that area. But really, I love the problem solving and I love the mysteries. And I could not get enough stoichiometry problems. Like, I just love them. And it's reflected in really my molecular literacy approach to chemistry because that's the part I love the most. I could do problems for hours and I would just keep doing them and I would do extra problems and solve them. And I just thought it was a fun puzzle. I just had that kind of give me more when we got to equilibrium expressions. I thought, wow, this is fun. And these things called the ice tables. And there's all these things we do in different genres of chemistry that were just fun for me. And then in the laboratory as a high school student, I have quite the nose. And when they gave me knowns, I just smelled them. I know you're not supposed to, but I'm like, well, that's wintergreen. It was pretty easy. And my family today still remarks upon it. They're like, "Mom, you smell everything." I'm like, I know, it's both a blessing and a curse. But I do have quite a nose and a sense of smell, and helped me to kind of bring an extra sense into a chemistry lab. You have the visual components of it, you have the problem solving. When you get some things, that's kind of cool too.
So those initial experiences, so the academic validation and getting to like smell and have tangible interactions with chemistry and getting to view chemistry problems as a puzzle. Do you remember anything that was related to kind of validating that specific perspective that these chemistry problems are a fun Sudoku-like puzzle that you enjoy doing? Something that like really helps set the stage because some people see these and they see them as these exercises that's kind of a chore, and
Mm.
other people will see them as like a really fun puzzle. So what do you think helped you develop that perspective?
I was raised in a family of readers. My grandma worked in a bookstore. And so from the time I can remember, she was bringing me books. And she got me hooked on Nancy Drew, and then she got me hooked on Encyclopedia Brown and Agatha Christie. And so this genre of mystery and solving puzzles And that was something we would share. So we would read an Agatha Christie together. I remember the first time I read Roger Ackroyd, I was blown away. Like, it's one of Christie's seminal pieces, and it's just so amazing. And we would talk about it, about who did it. And then we would watch some early television shows that were mysteries. So this puzzle building and solving mysteries came from being a prolific reader. I read all the time and still do and really enjoy it. So I think that neural pathway was open to me as something that was joy, as opposed to something that was dread. It's like, oh, here's another mystery to solve. I love solving mysteries. And so the chemistry problem sets pose themselves just like that, as getting an unknown in a laboratory. Like, whoa, this is real world. This is just like Agatha Christie. Let's go.
Are there elements of puzzle solving and whodunit in your comic books now?
Oh, yes. The whole series is based on mysteries. The first book is called The Case of the Deadly Dials. They're case files. And you go back in time to try to save the radium girls from being poisoned by radium as they paint the dials with radium, missing atomic model. And that's where Niels Bohr has the quantum mechanical model of the atom locked away because he wants the Bohr model to be the only model that exists. You have to use the number of protons, neutrons, and electrons to get the quantum mechanical model out. There's a case of the pillaging pirates that's based on The Princess Bride. It's a complete parody on the Princess Bride movie, where Lady Xenon is being held captive for 1 million electrons by the dread pirate Clive Green. And her true love, Sir Carmen, the 6 electron man, has to come save her. And so you go on, but each one is the case of with the mystery involved.
Are these resources just for teachers to buy, or can anyone go and purchase them off of a website? Like, how do you get involved with reading these?
They're on my website and they're for anyone. We offer them as class sets, and I've got something called the Molecular Literacy Bundle, which is the set of comic books, but also there's games, puzzles, and activities that kind of enhance that fun with periodic table twister. And then there's recipes that align with the comic book lesson. So when we're talking about ionic compounds, there's a recipe for chocolate chip cookies, but it talks about why we add salt to chocolate chip cookies, because it seems like an odd ingredient when you think about it. And then there's a card game called Ionic Ooze, where you try to create ionic compounds. It's a little bit like Uno setup. So there's a whole array of things on my website, and you can visit there. And there's also 108 pages of detailed lesson plans for teachers out there. So if you're intimidated and you're in that crew that either avoided chemistry, didn't like chemistry, the lesson plans are broken up into as small as 5-minute chunks about how to approach the next lesson.
It's incredible. Why do we add salt to cookies? Because I was always told it brings out the sweet to have the salty. But, I just kind of accepted that as conventional wisdom and I never questioned it.
Me too. I had to look it up for this. I had to do a little deep dive as an older chemist. It has to do with the gluten in proteins. And as you know, salt can disrupt hydrogen bonds in a protein. And so it adjusts the shape of a protein enough to make them chewier. Baked goods without salt aren't going to have that. So you need to disrupt the gluten proteins just a little bit, to them change their shape a little bit. So it works like that. Who knew?
So when you moved forward, right? Now we're going forward in time and you're there starting this incredible research project as an undergraduate. What was the thing that had never been done before?
The professor that I was working with, she was an organometallic chemist, and she was looking at iron bonded to silicon as opposed to carbon, because organometallic compounds usually are a metal bound to a carbon. And so we had an iron silicon complex, and we wanted to do an elimination reaction where you abstract a hydrogen to create an iron silicon double bond. And that iron silicon double bond hadn't previously existed in the world.
What was the outcome of that?
I never finished it. I never accomplished that. We got pretty close, probably almost a decade, I think, before that paper was published, between all the undergrads working on it.
You do all of these incredible outreach initiatives, educational initiatives. Is there any one thing that you have done that has had the most evident impact on people being able to envision themselves as scientists?
Definitely, when I retired from the University of Arizona in 2023, I think this is pretty common, but I had a pretty short retirement, 4 months. I don't know if that's a world's record or not, but it was pretty short. And then I became an elementary school science teacher during the past few years as a pre-K through 4th grade science teacher. I'm really able to see how brilliant these kids are, and it's all kids. And they love big league science, and that's the way I describe I can talk to them about a single replacement reaction when we're talking about the case of the deadly diodes and the radium girls. And I'm like, "Why did they get sick?" And they said, "Well, down here and calcium's up here, so radium must have replaced calcium in their bones with a single replacement reaction." And then they write out the
Wow.
reaction and they balance it. And they're seeing the puzzle joy, right? They just read a mystery. I'm presenting them a puzzle. They can take the letters, as they call them, the symbols for the elements, and they can see the story in that. And so our new readers are really great at looking at the periodic table as just a new alphabet. They just learned the alphabet a couple years ago, proficient at the English alphabet, and now, hey, here's just another alphabet. So I just love watching them dive into the book and read to each other and write down things. And all the time they're looking at the periodic table like it's a treasure map with clues on it. And it's just so fun because I can see that when they get to chemistry, they're going to have that warm fuzzy, right, about that. And when they see a periodic table, what a great memory they're going to have in high school instead of like, what is that? I'm scared. Everyone told me this class is horrible, right? I'm giving them that
Yeah.
solid, warm fuzzy in the tummy that never goes away. And I just am so excited. And I want all children to experience that so that when an adult says, oh, that I didn't like that class or it's hard, they're going to be like, but it was fun. So I want to dislodge that basically chemistry needs a whole new rebrand across the board. So people think of it as doable and fun and not just for whatever smart. People say, oh, well, you must be smart if you do that. It's just doable and fun.
So most of our listeners are research scientists who are looking for ways to broaden their societal impacts. I imagine if you polled our audience, the majority of them would say that they weren't exposed to chemistry as a concept or a discipline until high school.
Right.
How critical do you think it is to expose younger children who are, like you said, have just mastered the English alphabet to chemistry and to the periodic table?
I was teaching organic chemistry for 30 years, and I have the brightest of the bright. Undergrads who are taking organic chemistry aren't usually taking it for an elective. And I'm looking at these brilliant students semester after semester, 100, 300 students in an auditorium. And semester after semester, this is their first, what they define as a failure. And again, a failure for them could be an 80. So I'll let them define their failure. But whatever it is, it causes tears, it causes anxiety, it causes them to change their major, rethink their dreams. It has thwarted so many dreams of whatever. There's 50 college majors that depend on organic chemistry, and that's usually an A or a B. Medical school is definitely an A. This is not the case where these students are lacking effort, lacking academic confidence. They're not lacking anything, but what they are is they're molecularly illiterate. And then I start to think, what if these students said, hey, I'm going to go to college and I'm going to major in music, but I've never played an instrument before. I've seen a sheet of music for a semester in high school, but I'm going to go and I'm going to major in music. You can't do that. So if you're going to college to major in music, you probably started playing an instrument at age 5. So mastery is something that's over time. And then if you think about if we decided to teach the alphabet to kids in high school, and then they go to college and say, oh, here's a Hemingway novel, read it and analyze it. And they had just learned how to read. We know that literacy takes time and practice. So my research has shown that molecular literacy takes that same amount of time and practice. It's just when you're cramming it in, the only thing these students have to quote unquote do well is mathematical skills, because those have started also at age 5. So they rely on math, and that's why people think that chemistry is only math, because that's the only language they have. If you are illiterate, you're going to take any workaround you have to get through, especially when your dream's on the other side of that. And so when you get to organic chemistry and there's no numbers, whoa, all of a sudden I have nothing. There's nothing I recognize. And my brain has never been trained in this way. So how am I supposed to do this? And perhaps your listeners, if they've taken the course or taught the course, know that it comes at you fast and furiously. And so
Yeah,
they're
definitely.
left to memorize things. They literally have to memorize all of it. And after a while, that just becomes fragile and falls apart.
It explains a lot about why it can be such a dreaded and gaping course, organic chemistry in particular, but also general chemistry. Like you mentioned, it limits so many careers. And I can't tell you how many times I've introduced myself as a chemist and I've gotten the response of, I hated that class. And it's heartbreaking because it's like,
It's
I understand why, truly I do. Like I struggled with it as well. But somewhere along the way, I learned like, oh, this is the explanation to everything.
yes.
This is how we understand the whole universe. And once I understood and appreciated that, and I wanted to start picturing it in my own mind, I went rogue and it was no longer just doing the course. And now I wanted to learn about, okay, what is the process behind this? What does it look like? What does it feel like? And it's one of those things that I had to go beyond my course to find. And maybe it shouldn't be that way. Can you share some examples of how this like math-centric approach to chemistry hinders student understanding, interest in chemistry, career development? And if you could add on to that, like what are some alternative approaches that you've found have been effective to helping students get beyond this like math workaround in college?
I'm tutoring a gal right now who's taking Gen Chem 2, and we're calculating. We are using numbers. Kinetics uses numbers, and I love all that. The numbers and the math are just part of it. So when I'm working with a student and when I'm teaching my own college course, especially in Gen Chem where there is a quantitative aspect, I work on their intuition first, and I call it their chemical intuition. If you know that equilibrium is products over reactants, right? There's an expression like that. So what's favored if the numerator is big? What's favored if the denominator is big? And then just kind of work on your intuition about, is the number going to be big or little? Try to predict an outcome without relying on your calculator. I try to teach as much as possible without a calculator. Like, just tell me what's going to happen. Tell me about the magnitude of the number without knowing it's 4.57 times 10 to the minus 20. Who cares what the number is? Just tell me the magnitude of the number. Really big, big, small, really small. So put the thought back into it. And it's also really important because I have seen so many times calculators. I don't know, they got all these parentheses. I watch the kids. They're like, can you help me with my calculator? I'm like, oh no. I'm like, my calculator is like $10 and the buttons are as big as chiclets. Like, that's a gum candy for those who don't know. This is what I
I
use.
love chiclets.
That's what I use. And they're shocked. And so sometimes their calculator order of operations comes out wonky, but they still write down the answer because they're more confident in their calculator than they are in their intuition. And I want to flip that always. Like, you predict the answer, you get that solidly in your head. And then when you go through your calculator, you can be like, hey, something's wrong here. That's not what I expected.
That research study that I never got to publish about how we asked all of these undergraduates in Gen Chem 1 and 2, what is the mass of the products before the reaction begins? And only one who was educated outside of the country was able to answer that it's 0 because the reaction hasn't begun. So there are no products. And a lot of the respondents understandably said it's going to be equal to the mass of the reactants because they were memorizing the law of mass conservation. They weren't able to picture the process of having a group of reactants interact and then developed products over time. It kind of all existed in a big jumble. And that to me sounds like another example of using math to kind of get around the actual conceptual process of chemistry.
I think as we're saying that too, my students to draw a lot. If we're doing thermo, we're drawing the system and surroundings, we're drawing what's happening. So we do a lot of drawings. If we're looking at transfer of heat and we have two metals beside each other, draw the two metals, and label them. And it just helps them to think a little bit more deeply. Do they need the drawing? Maybe not, but I think some of them do. And again, we're trying to elevate molecular literacy. So things like drawings help with molecular literacy as opposed to just relying on quantitative function to get the right answer and having no idea of what that even means, but you got it right.
You've journeyed from this kind of like environmental toxicology research to 30 years of teaching freshman chemistry and organic and working with kindergarten through fourth graders. You taught chemistry along so many continua that most people don't get to see. What insights about teaching chemistry have you gained from working with the little ones that you wish you had known in your university years?
The little ones are fascinated by the periodic table. I have a big periodic table shower curtain in my classroom, and they'll sit there under it and just stare at it. And they will have so many questions. And they'll go up there and they'll point and say, "What does this one do?" And they want to know the stories and they want to know. I think as adults, and especially in elementary education, oh, that's too much. We have that feeling like that's too much. We don't want to push them. It's that. Let their curiosity guide them because that curiosity brings them joy. So for me not to tell them the story of an element if they point to, it's heartbreaking to them for me to say, "Well, I have it up here, but you'll learn that when you're in high school." Why? Tell them the straight truth now. Tell
Right.
them now how it works. And as much as they can understand, they will understand. They're so, so curious. And I think it's incumbent upon us as educators of these younger students to really foster that and answer it with really good science, not hand waving and say, "Oh, you'll get that later in life," or "We'll talk about that later." Now is the time. They're asking the question now. Answer it.
For the college chemistry professor who's listening to this and thinking about like how can I best help my college students from the information that you now know about educating across those age ranges, is there anything that you could offer?
I think what I would have told my younger self is that they are molecular literacy. This statement that they should know this, if they're asking the question, it means they don't know it. So answer it, explain it, and understand that what you are presenting, whether it's on a whiteboard or a screen or however you're presenting, they can't read it. They literally cannot read what you're putting up there. And it is hieroglyphics and it's scary and it's intimidating. And to meet them with that and say, "Okay, this is what you're seeing, this is what I'm seeing," and trying to meet that. I think about the exams that I created where I would see the problem one way and think, "Oh, this is such a cool question for an exam." The students would see it and have no idea how to approach it, even though I thought, "Oh, they'll know how to do this." 1 year with chemistry is not enough. So this notion that even if they had high school chemistry, they're not going to be able to keep up for the most part. We have a 50% failure rate in Gen Chem. And again, failure is C, withdrawal, D, drop, all of these things. So obviously there's a problem. And the problem is the textbook or the instructor or the student. The problem is illiteracy. Once you recognize that, you can't unsee it. And I think all faculty, I would recommend that it's going to give you a better connection with your students and ask them questions of what are you seeing and explain to me how you're seeing it so that you can meet them and start to develop that literacy, even though you've got a lot to teach. So it's hard. I get the challenge. That's why ideally we start at age 8.
There's not a lot of examples where a 50% failure rate would be tolerable, like seat belts, birth control, planes, plane travel, engine success and turning on. Like there's just very few spaces in the world where it's okay to have a 50% success rate. And what's uniquely frustrating to me about chemistry is that it's almost celebrated
Yes.
as, well, we're thinning the herd, we're like cream of the crop, all these elitist kind of ideas. Do you have a perspective on that that you'd want to share?
When you look at organic chem, we have an 80% failure rate. And again, this hasn't changed for like 30 years for underserved students, or underrepresented students. 50% for the general population, but when you're specifically looking at underserved students. And then when you think about that prohibits them from becoming a physician, an engineer, a scientist, a dentist, a physical therapist, then it becomes an issue of civil rights. If we have one course shutting the door down on access, how are we not questioning that as a society as an issue of civil rights? What is happening here when we've got this demographic that, again, and this becomes from coming from areas where their school may not have been able to afford chemistry, right? Chemistry is an expensive course to
Right.
offer in a public school because of the labs, and some of the teachers are not available, all of that. So maybe they had nothing, and yet, or it just shuts them down. I think the idea of a weed out course, yeah, definitely. I know I'm sounding a little radical here, but for me, that is on, okay, is that an issue of civil rights? Because who
Yeah.
are we weeding out? Let's look to see who we're weeding out with this course. That's really, really concerning to me. And I'll go to my last breath trying to undo all that injustice.
When I was doing my research for my dissertation in chemistry education, I pursued it with a critical lens and was thinking about who are we excluding. And I decided to play with the statistical model that predicted who would pass and who would fail. And I entered in my demographic variables. So first generation American, first generation college student, woman, Latina, autistic. And my likelihood of failure was in the high 90%. And it was one of those things where I was like, okay, why? Like, there's nothing about any of those variables that should imply that I wouldn't have just as equal opportunity to succeed as anybody else. And to be fair, everyone across the board received like a 60% likelihood of failure rate because of what you've described, right? But for it to be so much higher for somebody with my combination of identities, I was exploring those ideas of intersectionality. And so I was exploring those concepts, and it just made me feel lucky that I had survived, but wish that it didn't have to be something I survived.
When we consider all that, how can we change it? And then when we think about the problems of literacy, and that those still exist, but address it more as a literacy so we can capture more. And literacy is also like, my books are available in a library. You can go to a library and get them. So the accessibility of them it doesn't require a lab. It doesn't require anything else. And I think also when we're looking at chemistry in college, we have to understand, and this goes to the K through 12 educators and those who are developing K through 12 curriculum for chemistry, 80% of the students' grade is lecture. So 80% of their grade is molecular literacy. The other 20% is lab. And the K through 12 in general seems to have it flipped. Go to the STEM camp and make slime, go to the STEM camp and make a volcano, whatever. None of that helps. He could be the best volcano maker in the world and still fail Gen Chem. It really comes down to what is the story in higher ed? And if K through 12 is not actually preparing them for that, if they're just putting them in lab coats and safety goggles and saying, you're a scientist, it's not a fashion show. It's not a costume. It's up here is where it has to happen.
This makes me think of your TED Talk. You were focused on communicating molecular literacy through storytelling and describing the universal language that can make chemistry accessible. Could you share an example of how you've used storytelling to help students understand complex chemical concepts?
I have my own comics and my own stories, but prior to that, I defaulted to storytelling out of an act of desperation. I didn't really have the eyes for the molecular literacy component yet. I was still a new faculty member trying to figure out what was happening. But I knew that they weren't seeing what I was seeing. I just didn't know how to articulate that. I thought, what can I do? And I was a new mom at the time, so I had access to a lot of characters. And Winnie the Pooh was high on the list at the time. So I thought, if we look at a substitution reaction and we consider the leaving groups, which are the group 7 halogens, so we've got fluorine, chlorine, bromine, and iodine, and there's different rates that they can, or abilities for them to leave, and that it impacts the rate of the chemical reaction. So I thought, if I explain that fluorine's like Piglet and holds on to that carbon really tight and is not going to leave and is afraid to leave, and if we go down to bromine, bromine's Winnie the Pooh and all just like roly-poly and again, polarizable, like bromine's huge and polarizable. But bromine's all roly-poly Winnie the Pooh-like and will just wander off in 100-acre woods all by itself. Then they're able to see that. So then when they see fluorine, they see Piglet. And I even did some slides that had that up on there so that they could see, okay, yeah, this is what's happening. And this is why these rates are not the same, because of the ability of the leaving group to leave and for that substitution reaction to continue on. So just lots of different characters over time have served me. I had a Shrek time in my life where every example was from the movie Shrek. It just depended on what was contemporary. And the magical time, I think, for my teaching is when the students I were teaching were the same age as my son, because then I could really relate to their childhood. And I say, "Do you guys remember watching Blue's Clues?" I'm like, "Yeah." I'm like, "Okay, let's talk." All of that relatability is just storytelling and image creating because they don't have that capacity. No one built that for them yet.
You mentioned earlier that one of the great joys is telling the students what the stories of the elements are. Is there one element story in particular that you really like telling?
I think that they just love is Alice in Wonderland and the Mad Hatter. So I take the time at the beginning of a semester in a college course to talk about the elements and tell these stories. And now I'm taking the time with my fourth graders to do the same. But I take the time because they love these stories. So I talk about, in college, I even had a case study about the vats of mercury and how the sulfur-rich proteins in the animal pelts were attracted to sulfur because they're called mercaptans. And so the sulfur and the mercury bonded and all of that. But I talk about the Mad Hatter and say, was he mad because he's angry? Or was he mad because they were saying that he had some neural disorders? And they're like, yeah, I think it was the neurologic kind of mad. Like, what caused that? And like, I don't know. I'm like, well, he actually was making hats with vats of mercury. And then we talk about all of that and what is mercury, and then talk about how sulfur and mercury are attracted to each other and how that process works. But all in the lens of a favorite Disney character, the Mad Hatter, and a story, Alice in Wonderland, and what that all meant. And then go into, of course, my environmental toxicology. And then, of course, there's tragic stories that are more contemporary with mercury. So I'll go into all of that.
Yeah,
And some of that I lighten up with the littles because they don't need to know some
of
of
course.
yeah.
You don't want to make them afraid of the lab. Yeah.
Yeah.
Yeah. Safety first, but
Yes.
fear last. That makes a lot of sense. Could you connect one little bridge for me within that? Like the mercury, sulfur attracted to one another. What is it about that that drives somebody mad? There's proteins involved. What's happening there?
So it's the reason they use mercury because boiling mercury nitrate is an effective way to remove hair from skin
Oh, okay.
because the sulfur proteins in the hair are attracted to the mercury in the vat. But it's the mercury fumes themselves that are causing the neurologic disorders.
Could you help me understand how storytelling is uniquely useful in helping deconstruct the barriers around chemistry being a gateway course?
Stories stick, and that's something that's become more and more popular. But stories allow also for intergenerational learning. They allow for collaborative learning. When my students are reading the comic books, they often take a character and read aloud to each other. There's all kinds of neural pathways that are opening while they're learning chemistry that don't really have to do with chemistry per se, but they have to do with a message sticking in a joyful environment. Storytelling creates impact, it creates joy. And when you've got those things going on, it creates a space for imagination. Maybe if you're looking at chair cyclohexane and you don't know what the heck's going on, like what is that thing? And your professor's up there twisting it and saying it's a boat and it could flip. Even with the model, they can't see it. Make it something that they can bridge to and call it a lazy boy chair. And then say, what would happen if the lazy boy came up on the other side, right? Then they're like, oh, okay. So storytelling, putting a vehicle to get to their imagination so that the molecule can then become something that they can see is, in chemistry in particular, is what storytelling does. So it builds all of that, but definitely the imagination part, I think, is the most important.
As a species, that a lot of our success, arguably, evolutionarily speaking, is because we tell stories to each other. And there's so many ways that we bond and connect and can grow beyond what our knowledge in that one time period is through stories. So it just makes sense that that would be helpful. What do you see as the biggest sort of systemic barrier to implementing molecular literacy at a younger age?
I think it's a whole rebranding. And when I think
Yeah.
about it, it feels like I'm pushing a ginormous boulder up a hill, people on either side of
Yeah.
me clapping and saying, what you're doing is great, but I need help with the boulder, folks.
Yeah.
It's great for you to clap on the sidelines, but I'm still pushing it up. and really just needs a rebrand. I give it a try. If we all get behind this boulder and start pushing it up, it'll get lighter. But right now there's this, well, that's a high school course. And even my closest friends who are chemists are still like, well, blah, 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 it should, be taught like this and like that. And if we look at the data like you collected and that I collected, 50% failure rate. Why are we still doing this? Try something completely different and see if we can do it. So if you've had a trauma with chemistry, which is more folks than we would, I mean, if you're getting that and I'm getting the, oh, you're a chemist, oh, I hated that. That's really a trauma
Yeah.
response. I mean, if I'm at a 4th of July picnic and someone's telling me about a course they hated 30 years ago, that's
Right.
trauma. Because if you remember a course I hated 30 years ago, but they do. And I'm bringing up everybody's trauma. And so I have had parents saying, just get through it to their children. We've got to get rid of all that ick and let's just get rid of it and start again. And it's folks letting go enough to try it and get rid of the ick and see what happens. Because I think we all agree we want global community of molecularly literate citizens. That's the goal. Why do we want to gatekeep that? I don't understand.
My way of helping you push this boulder is gonna be my own shtick about how I can't stand that chemistry is taught with stick figures when these molecules exist in 3 dimensions. It drives me absolutely insane. But I also understand, like, we're not 3D molecular animators. There's probably 5 of those in the whole world. I don't think I could even include myself in that, but I would probably say that because I've spent a few hours on it, I have some of those skill sets. And it's difficult and time consuming, but the more we can start making that transition so that the students can appreciate how these actually look and rotate them and get to actually visualize them. Like, what other field do we teach with stick figures? Is there any other field? So I'm committing to helping you push that boulder. And if anybody is listening to this, like, I'm helping push the boulder. I'm sure it would mean so much to Colleen and I if you just wrote a comment and told us how you are uniquely helping us push this boulder. Well, we're in our closing tradition of the podcast, and I'll say that our last guest, Bradley Olson of MIT, he had questions, and his question is, what role could scientists who are also leaders in fashion, art, or other domains play in advancing science? Because he was observing that it's very rare that you see a scientist pushing the boundaries on fashion or serving in governmental roles, but also being a scientist. Usually, being a scientist is, encapsulates most of what a person's like, personality is, it feels. And every now and then you see someone unique like yourself who brings education in science or fashion in science or cooking in science and brings them to the fore so that people can connect with it in different ways. So how do we encourage more people who are scientists to participate in these hybrid science and other interest spaces?
As a research scientist myself, years ago, I wouldn't have looked at fashion. My son's a fashion designer now, so now I am looking at it because I live with the fashion. He does screen printing, and we talk about the process of screen printing, and there's a lot of nasty chemicals that are still, maybe it's not universal, but at least in his realm, that have been used in screen printing, especially cleaning the screen. So I would recommend that any object you look at, any venue you're at, if you're at a movie, like think about like, what does this film look like? What's the science behind it? There's science behind everything. There's molecular literacy behind everything. So instead of kind of thinking science is for disease and for energy and then for helping the environment, look at it all around. And I'm going to give a shout out to a collaborator that I have, Josh Smalley, who was the 2023 runner-up at the Great British Baking Show. Josh is a PhD chemist, and Josh is also doing a great job. And everywhere he goes, he tries to put the chemistry of baking in front of people. And even in the Great British Bake Off, he made a cake where there were molecules all over it. And he's just doing such a great job with it. So stuff like that is great.
Well, you were asked a challenging question, so it only seems right that you get to ask a challenging question. So our next guest, his name is Caesar. He's a multimedia content developer for Howard Hughes Medical Institute.
I would ask Caesar, how do you bring the scientific method inquiry into a descriptive discipline and a descriptive format, right? So, how do you capture your audience with maybe a mystery or maybe a question that's unanswered to kind of build intrigue? As a scientist and you're working for HHMI, how do you bring that in there? How do you make it juicier and bring that kind of yummy science in there and differentiate your way of producing that way?
Why should our audience, who are research scientists looking to broaden their societal impacts, listen to our conversation today?
I think it comes down to that we're all on the same team and we all recognize the need for a rebrand. And molecular literacy gives grace to everything that's happened before. When we recognize that these failure rates and these trauma experiences and all of this is a result of a literacy problem, which is significant, but we know now that we can circumvent it or get around it or address it. That's why they should listen to it, because we all need to be part of this rebranding and we all need to understand, okay, if someone has a bad experience with chemistry, it's probably because they're molecularly illiterate. How can I explain it in a way that's literate? And how can I build that? So, how would I explain something to a child who can't read a book but needs a story to be told to them?
Thank you for everything you've done to make science more impactful.
Thank you.